Electrochaea is commercialization a grid-scale energy solution incorporating modern science and single-celled microorganisms billion of years old. Our next speaker will talk about sustainable energy transition and how biological methanation contributes to the circular bioeconomy. Please welcome Development Director of Electrochaea, Birgit Lewandowski.
Thank you very much. So first of all, thank you very much for inviting me. Very kind, and also congratulations to the great conference here, namely to the organizers, namely Ilona and Kaspar. So here he is, Kaspar. Thanks a lot for invitation. So I will talk about carbon capture and utilization method. It's going wrong. Yeah. Oh. So he doesn't have magic hands either. I can use that one. It's also fine. Okay. So and I will also target the question of renewable energy within my talk. And before I start with, I would like to give a general overview. I will talk about energy and energy storage, especially from renewable energy. I will talk about the overproduction of renewable energy, the generation of renewable transportation fuels, decarbonization of gas grids, and also the large-scale carbon use, which is the link to the current session of the carbon usage in the biotechnology. So let's have a look. Let's start with the whole value chain. On the left side, we are also using electricity, renewable electricity preferably, for generating hydrogen. And we are also using carbon dioxide as the only carbon source. So I'm not talking about organic carbon sources, but from the inorganic carbon source, the carbon dioxide. And with the proprietary technology of Electrochaea, with the biocatalyst, we are creating in our factory, in our reactor, methane. And this methane, this renewable, methane produced by renewable sources from CO2 and hydrogen. This power, the gas technology is the core here. And this can be, this methane has, there were some strange vibes here. Can be the production, we're producing gas grid quality of the methane, and we are producing also oxygen and heat. And that means that energy, overproduced energy and also CO2 can be harvested into a valuable molecule. I try now. This one. Oops. Okay. Good. So with renewable electricity, we have to have in mind that we have also a very fluctuating energy market. That means we have times with overproduction, and that means that electricity has to be stored. And when it comes to the question of storage of electricity, the first what comes to our mind is our batteries. But on the other hand, we have to think also that not each and every technology fits well. We have to take into consideration the amount, the capacity, what we want to store, and also the time frame. So batteries are very good energy storage systems if we are talking in a comparably small scale. But when it comes to large scale, a high amount of energy to be stored over a long time period, we are reaching up to hydrogen and to methane. When we want to distinguish between the pros and cons of hydrogen and methane, Both are long-term storage, suitable for long-time storage. But one advantage from the methane is that with the gas grid already established, the infrastructure is already available. In contrast to that, with hydrogen, hydrogen is a very small molecule, as we know. So the prerequisites of storage and also for implementation of the infrastructure, which is not available widely currently, that is a very high, very cost-effective, cost-intensive also. So we can use, when we want to store and also transport energy via methane, we can use the existing gas grid. Wow, okay. And now, a quick look on this circularity. On the left side, the red dot, again, the electricity, and then the carbon source. Carbon source can be taken, essentially, the carbon dioxide doesn't matter from which process it comes. When we are thinking of carbon dioxide within the biogas, from the biogas plants, we can use it directly because impurities in the biogas, which are mostly sulfur and also ammonia, are also some nutrients for our biocatalyst. Other carbon sources from industrial processes it might be necessary that they are purified, although the biocatalyst is quite robust and also can handle with a lot of impurities. So both are fed into the methanation process, and as well the hydrogen creates heat, and also the methanation reaction itself creates heat. It's an exothermic reaction, and this heat can also be used either on-site or also in the gas grid. And the produced methane can also be injected into existing gas grid, used for heat, used for transportation, can be used for household. And on the other side, it could also, as a green methane, used in power plants if we need electricity on the other hand. So that is the circle. And as well, the heat and also the methane, on the other hand, could also be used on-site. I would like to give you an example. When we're looking on a wastewater treatment plant, for example, and they have a biogas fermentation facility on-site, they could use also the methane on-site, for example, for using electricity and heat in CHPs, for example, with this upgraded methane. And also the oxygen from the electrolyzer could also be used in a wastewater treatment plant for enhanced aeration in the biological treatment. So quick introduction about the technology. Here a fermenter, it's really as green. So the biocatalyst liquid has exactly this color as long as our biocatalyst feels happy. But generally speaking, first of all, we are subdividing the system into two steps. We call it the two-step process. On the left side, the electrolysis is not part of our technology. That's the classical electrolysis, and we are just using the hydrogen. And on the bottom, also the CO2. So our technology, proprietary technology, starts somewhere here in the inlet when hydrogen and CO2 are mixed in a ratio of 4:1. And within the fermenter, the bioconversion to methane takes place via gas fermentation. The fermentation process runs of about between 62 and 65 degrees. It's an exothermic reaction, as I told you already, so we had to remove and extract the heat from the process. And typically, we are also working with pressurized reactors, so the whole process is conducted under 10 bar pressure. And on the top side of the reactor, there's this outlet gas, which has to be purified if we want to inject it into the gas grid. Purification has to be done mostly for sulfur and also for ammonia. So again, here. And so the advantage of using a biocatalyst is that we have, this is in the biocatalyst as a single cell microorganism. It is continuously replaced within the reactor. So when we are thinking of a classical chemical catalyst, the efficiency decreases over time. A biocatalyst, which is growing and subdividing, is always fresh, let's say, in the fermentation broth. But on the other hand, we have to feed them with some nutrients, with some salts. And yeah. Okay, and we are not using bacteria. So our biocatalyst belongs to the domain of the so-called archaea. So for the microbiologists under within the audience and the nerds about it, this archaea, they are a separate domain besides of bacteria. And they belong to the eukaryotes, and they are closer related to eukaryotes than to bacteria, more or less, and they appeared on the planet a long time ago. So they have been one of the first microorganisms on planet Earth. And yeah, they occur in hot springs, for example, sulfur-rich hot springs, and also volcanoes, geysers, and they are extremely resilient. So that is one of the advantages, that this biocatalyst is extremely robust. Ours is growing also quite fast, so we are working typically about in an optical density of around 30, which is really a very thick broth, let's say. And yeah, and with this technology and with the greening of the gas grid, we are currently implementing that into, and we are currently in the rollout of the commercial application. Again, short overview. With this renewable energy, we can store renewable energy during periods of low supply in the gas grids. And let's go, oops, what happens now? Back. Yes. And the power grid operators can also avoid some capital expenditures because we do not need any additional adaptations. Some communities can use it also as a puzzle piece to store energy and to reuse it when necessary. And we could also use carbon dioxide from landfill gas, for example, landfill sites, wastewater treatment plants, fermentation processes like dairies, and also biogas plants typically. Yeah, substitute, I think we've already done. Currently, since we are commercializing the process, the first plant will be built in Denmark, in Roslev. It will be a roughly 10 megawatt a plant. That means that the electrolyzer has a 10 megawatt capacity, and we had to calculate the greenhouse gas, so the carbon intensity for that. And just to get a rough idea what such a 10 megawatt plant, which is a very small plant, because it's the first commercial plant, will be the first commercial plant in the market, we can avoid about 15 kilotons CO2 per year. And that is comparable. I like the elephants most. So the weight of the CO2 is approximately 3,000 elephants. And when we scale up further, so the first biocut plants have been in a 1 megawatt scale that were pilot plants. Our current first commercial plant is a 10 megawatt plant. And the 50 megawatt, we have already scaled it up and designed the plant, and we are currently developing some projects in Europe and as well as in USA for this size. But when we have a look into the future, up to 250 megawatt, 250 megawatt, we can see that we have it is a really good tool for an avoidance of greenhouse gases. With our main investor, Baker Hughes, a global player in the oil and gas industry, we are jointly developing the technology further, and also we are implementing it, and with this investment of Baker Hughes, we are able, as a technology provider, very comparably small company, with this big partner, we are able to roll out the technology worldwide. Electrochaea, when I started at Electrochaea 4 years ago, we were about 28 people. Now we are roughly 60, so we are growing quite fast. Nevertheless, with 60 people, you're not able to do a commercial rollout. For that, you need your partner, which help you. Yeah, and with this, I'm happy to answer your questions. Thank you very much for your attention.
So thank you, Birgit, and we have.
Thank you very much. What is the main differences between the cyanobacteria and archaea?
Cyanobacteria?
Yeah.
Cyanobacteria are producing our autotrophic ones, as far as I know.
Yeah.
This is not an autotrophic organism. So it's the archaea, so the methanothermopacter, is not producing oxygen. The electrolyzer produces oxygen on a technical basis.
Yeah, okay. So that it is stages turned around.
Yeah. We have one more question.
Maybe I missed that, but do you get your CO2 over here? Do you get your CO2 directly from the air, or do you need it in a concentrated form, some sort of special feeding way?
So for the sake of efficiency, we need it in a concentrated way. That's clear. It's an anaerobic process. What we have to avoid in any case is oxygen. Also, this archaeon has a capability of tolerate a little bit of oxygen. But what happens if you push oxygen through this process is that first of all you create with the hydrogen and the introduced oxygen water. And since hydrogen is the most expensive molecule in the whole process, it's a very expensive water. And also you have to think that the carbon capture technologies from air, this is one of our joint collaboration with Baker Hughes, with this ammonia chilled carbon capture technology that can be coupled. Or we use it in a concentrated way. For example, when we are thinking of a biogas fermentation, we can use it as it is. So we are upgrading the carbon dioxide fraction to methane, and the methane fraction of the biogas is only put through the reactor as a sort of inert gas. But on the other hand, from landfill sites, there can be also some impurities, some other byproducts which we have to test upfront and to check whether they have to be this stream has to be purified or not.
Yes. So what's the efficiency of your process in terms of percentages?
Yeah, we are turning 98.4% of this carbon from the carbon dioxide into methane. So this highly efficient Archeon we are aiming needs only 1.4% for building biomass.
Sorry, I meant the energy efficiency.
The energy. Okay, okay.
Yeah. What's the percentage of what you can get out of burning the methane?
What we have measured in the joule, not only calculated but also measured in our pilot plants, was roughly 70% of the efficiency.
So you can, if you burn the methane, you get 70% of that energy that goes into the methanogenesis.
Mm-hmm. Now, from the energy input to the energy output.
Yeah, that's what I meant. I mean, you burn the methane, you get 70% of the. Yeah. This is represents the 70% of the energy that goes into the methanogenesis.
Yeah. Yes.
Okay, great.
So do you have more questions? So thank you, Birgit, for your nice talk.
Yeah, thank you very much.